Hello, and welcome to the introductory video on ellipses. If you're just starting to learn about ellipses, or you are having some difficulty remembering all the parts, this is the right place for you. So let's start off with the definition of an ellipse. It's the set of all points. Remember, every point has an x and a y coordinate. We write them in a set of parentheses. So it's the set of all points in a plane, the sum of whose distances from two distinct fixed points called foci is a constant. Now, what does that really mean? Well, you get this kind of oval shape here, and if you pick any point on the shape itself and you draw a line segment from that point to both of the focal points, right? Focus is the singular, foci is the plural, and you measure the lengths of those two line segments and add them together, you're always going to get the same answer. That's what the constant is referring to. So whether or not you have a point there, a point over there, even over there, doesn't make a difference at all. When you measure out the lengths of those two line segments from the point on the ellipse to the two focal points, you're always going to get the same answer. It's not always going to be 5.4 in this example here. It will be different numbers, obviously, but it's always going to be the same answer for the same ellipse. All right, and again, the sum is constant. That's really, really the essential part of the definition there. So let's get into the requisite parts of an ellipse. There's a lot of them, but they're pretty easy to remember. So let's start off with the major axis, right? Major axis is the line segment that connects the two vertices in an ellipse. Vertices is plural for vertex. So you see those two vertex points labeled there on the shape of the ellipse itself. And I've highlighted the line segment that connects the two of them. In this particular example, it happens to be horizontal, but it doesn't need to be. Right? The two vertices, the focal points or foci, there they are, and the center of the ellipse all lie on this line segment called the major axis. And the length of that line segment is significant. It comes into play in a lot of different places, but especially in the equation of an ellipse. Right? The length of the line segment is significant, so let's talk about it. The distance from the center of an ellipse to either vertex on either side, we're going to label that lowercase a. And you're going to see that a lot. It's going to be in the equation, and it's going to be in a second equation, which you'll see in just a little bit. But just remember that point. A is always from the center to a vertex. Right? Now, because it's the same distance in either direction from the center to either vertex, 2a is the length of the entire major axis. Right? And that's an important relationship to know. That sum that we were talking about in the definition of an ellipse before, the sum of those two line segments is actually 2a as well. That's an important point for later on when you're writing equations of these things. All right, so that's the major axis. You can see another red dotted line there that's perpendicular to the major axis. That's going to be the minor axis. So the minor axis is the line segment that connects the covertices. That's plural for covertex. There's two of them, the endpoints of the minor axis, and we use a different lowercase letter to represent the length of that. But the minor axis also passes through the center just like the major axis does. The focal points are not on the minor axis, but the center is. All right, so that length or distance from the center to either covertex, we're going to call that lowercase b. And if you take the full length of the minor axis, that's going to be 2b. Right? An important little relationship to know there as well. So far we have lowercase a, that's the distance from the center to a vertex, and lowercase b, the distance from the center to a covertex. And once again, in this example we're looking at, the major axis is horizontal, the minor axis is vertical, but that doesn't have to be the case. The major axis can be horizontal, major axis can be vertical, or it can be Oblique, that's the fancy math term for a line that's neither horizontal nor vertical. And the same can be said about the minor axis. It can be horizontal, vertical, or oblique. It doesn't really matter. The ones you're probably going to be looking at for now are really just the horizontal and the vertical major axes. Don't worry so much about how you're going to figure out which one is which. You'll be able to tell from the graph or from the equation. If the ellipse is longer horizontally, it's got a horizontal major axis. If it's longer vertically or more stretched out vertically, it's got a vertical major axis. All right, the major and minor axes always have to be perpendicular to one another. That's something you need to remember. They form a 90-degree angle. And because they do, that right triangle relationship of the Pythagorean theorem comes into play here with those distances. All right. Now we spoke about A and B. Let's get to the distance from the center to a focal point. We're going to call that lowercase c. Right? Distance from center to either focus is going to be lowercase c. And although we don't really have a name for the line segment that connects the two foci, that's plural of focus, foci, it is still 2c in length. So that's an important relationship to know as well. So let's recap here the A, B, and C values and what they represent quickly. Remember, A is the distance from the center to either vertex. B is going to be the distance from the center to either covertex. And C is going to be the distance from the center to either focal point. And those A, B, and C letters, you should remember them from the Pythagorean theorem. That equation actually comes into play here as well, except we change it slightly. In the new form of the equation, I'll show it to you here, the hypotenuse, if we were to draw in a right triangle, the hypotenuse would actually be A. A is the longest of the three distances, A, B, and C. So we just rework the Pythagorean theorem equation a little bit, and this equation always works with an ellipse. C squared is always going to be equal to A squared minus B squared. Right? Definitely want to remember that equation. That will help you significantly. All right, so these A, B values, the C values, all of these things come into play in the standard form of the equation of an ellipse. And let me show you. It comes in two parts. One of them is for when you have a horizontal major axis, and you're going to see the A squared term is going to be under the X term, right? The denominator of the X term is going to be A squared if your major axis is horizontal. If your major axis happens to be vertical, the A squared is going to be under the Y term. Now, why does this really matter to you? Well, it becomes really, really easy for you to spot out whether you have a major or minor axis from the equation, because A is always the largest of the three distances, A, B, and C. So if your denominator under the X term is the biggest one, it's a major axis. If the denominator under the Y term is the biggest one, then it's a minor axis. Right? The H and K that you see in the parentheses with the X and the Y terms, those are the X and Y coordinates of your center. Just like in a circle, H and K becomes the X and Y coordinates of your center. And if your center happens to be at 0, 0, we don't write X minus 0 and Y minus 0. We just write it as X squared over A squared and Y squared over B squared, as it shows you on the screen here. So those are the basic parts of an ellipse. Those are the standard equation forms, whether your major axis is horizontal or your minor axis is horizontal, right? Either way. And all of those parts will help you identify, number one, how to graph the ellipse, and number two, how to write the equation of an ellipse from a graph, if you can figure out what the distances A, B, and C are.